All right, honors students, this could be a long one for some of you, especially if you didn't learn some of this last year in physical science. So really important that if you need to listen to this over and over again, you do. Pause when you need to write things down, because I will be moving pretty quickly through this because the majority of you I taught last year, so I know what you know. But you will notice a few new things. We're going to connect some highlights from chemistry last year and connect them to what that means for the study of life, which is biology. And then we're going to talk a little bit about some properties of water. That's really important to understand going into more biology stuff. So here we go. The chemistry of life. So matter, if you remember, is anything that has mass and occupies or takes up space. Everything in the universe is composed of matter. And kind of your elementary definition of matter is it's just stuff. So everything in the universe is composed of this matter stuff. What we mean by mass is that it's a quantity of matter that an object has. Now this is different from weight. Weight has to do with the effect of gravity on an object. So your mass never changes. How much stuff you're made up of never changes, but your weight does depending on where you're located in the universe and that gravitational pull. So that's an important distinction to make when you're making measurements between mass and weight. All matter is composed of tiny particles called atoms. A substance made up of one kind of atom is called an element. And so an atom is the smallest part of an element that still has the properties of that element. So we have all these different elements on the periodic table. You know, there's about 120 of them, and each of those elements, an atom is the smallest version of that. So I can have an atom of the element hydrogen, or I can have 3 atoms of the element oxygen. That's kind of what we mean with those terms. Really important you remember the structure of an atom because that really affects the nature of the element. Every atom is made up of smaller parts called protons, electrons, and neutrons. Those are the subatomic particles. Protons have a positive charge and they're located in the nucleus of the atom, the center. Neutrons have no charge, they're neutral. They're also in the nucleus. And then electrons are negative and they're in this electron cloud outside of the nucleus. So overall, the whole atom has a neutral charge, has a charge of 0, because protons and electrons tend to be the same total number, so they balance out. But the center of the atom has this positive charge due to the protons, and then the outside part of the atom has a negative charge due to the electrons. There are 6 elements on this huge old periodic table that you have to have for life on Earth. Those are carbon, nitrogen, phosphorus, hydrogen, oxygen, and sulfur. So those are really important. Majority of them are right here, but we got hydrogen all the way over here. So those are very important, and you're going to see them a lot, especially in Concept 3 as we talk about macromolecules. So remember, because we're referencing the periodic table, I want to make sure you remember what things are showing you on there. On the periodic table, you'll have the element symbol. This is a unique 1 or 2 letter symbol that just, abbreviates. So hydrogen symbol is H. That's just what we use to abbreviate it. There's an atomic number of the neutral element that tells you how many protons there are. Protons identify the element. So if there's a different number of protons, it's a different element. Number 1 proton, that is the atomic number, that means hydrogen. An atomic number of 2 means helium. So those are used to identify the element. This usually equals the number of total electrons also. Again, it's unique for each element. The atomic mass number is usually right here, it's this decimal number, is the average mass of an atom of the element. It's going to, usually be the sum of the protons and neutrons of an element. So when it's a decimal like this, that's taking in all the different versions of an element. It's giving me an average. So this is representing the mass number of the most common version of hydrogen. So we'd round that to about 1. Whereas when it's not a decimal, it's just a mass number. That's just protons plus neutrons. So protons and neutrons is the mass number. If I wanted to know just the neutrons, I could take mass number minus the atomic. So this number minus this. Because remember, again, that's my atomic number. All right, let's zoom in on the nucleus. This is the middle of the atom. It's a central core. It holds positively charged protons and those neutral neutrons. The overall has a positive charge though because of those protons. and it contains most of the mass of the atom. It's really, really dense in there. Looking at protons, all atoms of a given element have the same number of protons. So again, it uses the identity. And the number of protons is the atomic number. Again, in a neutral atom, the number of protons or positives is usually equal to the number of total electrons or negatives, which makes the overall charge 0. Looking at those neutrons, the number can vary in neutrons among atoms of the same element. And if there are different numbers of neutrons, we call these isotopes of the same element. So hydrogen 1 would be 1 proton and 0 neutrons. Hydrogen 2 is 1 proton and 1 neutron, and then hydrogen 3 is 1 proton and 2 neutrons. So this is just showing it's still hydrogen because there's only 1 proton in each of these, but the number of neutrons changes, which will affect the mass number. If you want to know what the most common of these 3 options of hydrogen is, if you look at the periodic table, the average atomic mass is 1.0079, which would round down to 1. So the most common version of hydrogen is hydrogen 1, which is just 1 proton and 0 neutrons. So again, isotopes, an element with the same number of protons but different number of neutrons. We see this for carbon 2. There's carbon 12, carbon 13, carbon 14. If we look at the periodic table, the average atomic mass of carbon is carbon 12.011. So carbon 12 is the most common version, which is 6 protons and 6 neutrons. So try this. Look at the periodic table. Take a second and answer each of these questions. What you should get for number 1 is based on the periodic table. The number of protons is based on the atomic number, and the atomic number of sodium is 11. Number 2, how many neutrons does fluorine have in its most common isotope? Well, if you look at the periodic table, it's going to be fluorine. It's going to have 10 neutrons in its most common version. What is the average atomic mass for oxygen? Let me get back and check that fluorine really quick. So if you look right here, it's 10 because if we look at this atomic number, it rounds to about 19, and there's 9 protons, so there'd have to be 10 neutrons. That is correct, 10 neutrons. Just want to make sure I told you that correctly. Let's catch up to where we were. Number 3, what's the average atomic mass for oxygen? That's 15.999. Or you could round that to 16. And then 4, what's the atomic number for phosphorus? That is going to be 15. All right, let's talk about those electrons. These are negatively charged. They're very high energy particles. They have barely any mass in them. They're so tiny. They travel at extremely high speeds, and they are located on different energy levels. Kind of you can see these little shells in this picture. These energy levels are different distances from the nucleus. We call this the cloud. The cloud's made of shells, and that innermost shell can only hold at most 2 electrons. The next level holds at most 8. Third can hold up to 8, and it goes on and on. We want these elements to have full shells because the more full they are, the more stable they are, and they fill from the inside out. The electrons on this most outer shell are called valence electrons. So example, in a neutral element of carbon, the atomic number is 6. So there's 6 protons and 6 total electrons. Remember, the first level only holds 2. So there's 2 electrons in the innermost shell. That means there'd be 4 in the next level, and that would be the most outermost shell. So there'd be 4 valence electrons. That means there's 4 places for it to bond with 4 other atoms because it really wants 8. It wants to have that full level. So the periodic table is arranged very specifically. They're arranged by their atomic numbers first. So you'll notice they go 1, 2, 3, 4, 5, 6, 7, 8, etc. These horizontal rows are called periods, and they tell the number of energy levels. So how many levels of electrons will there be in that cloud? Whereas the vertical groups are called groups or families, and they tell the number of valence electrons. So we just said carbon has 4 valence electrons. Well, it's in group 14. So everything in group 14 has 4 valence electrons, just like carbon, whereas things in group 1 have 1 valence electron. We skip these transition metals right here, groups 3 through 12, because, like the name suggests, they transition. So they're not as easy to predict, but these other ones are pretty clear. Group 1 is 1 valence, group 2 is 2, 13 is 3, 14 is 4, 15 is 5, etc. So molecules and compounds. Molecules are 2 or more atoms that are covalently bonded together. An example, O2 is oxygen. That's two oxygen atoms covalently bonded together. We'll talk about what covalent means in a minute. A compound is just two or more elements that are bonded together, so it doesn't have to be a covalent bond. So H2O for water and NaCl for sodium chloride, those are both compounds. Let's talk about compounds first. These have different properties than individual elements. So the elements that make them up are different from the actual compound because it's a chemical change that's occurring to form this compound. So NaCl is like one sodium and one chlorine. That makes table salt. So sodium on its own is incredibly explosive. Chlorine on its own can be poisonous. But when those react to make sodium chloride, it's table salt and you can eat it. So again, the properties of the compound very different from the individual elements. So what happens when the ratio changes? That matters. Right here we've got H2O, so two hydrogens for every one oxygen. Right here we have H2O2, that's two hydrogens for two oxygens. That's a really big difference. When the ratio of the elements in the compound changes, the physical and chemical properties change. You like to drink water, H2O. You do not want to drink H2O2, which is hydrogen peroxide. So that's really important. All right, let's talk about molecules. A molecule, like we said, has to have covalent bonds. Almost all the substances that make up organisms, whether they're lipids or nucleic acids or water, which we'll talk again more about, they're held together by covalent bonds. A molecule is a type of compound, so all molecules are compounds, but all compounds are not necessarily molecules unless they're covalently bonded together. So H2O, O2, O3, those are all molecules. Again, NaCl and H2O, though, those are both compounds. So let's talk about these bonds we've been mentioning. Bonds are like molecular glue. They hold atoms together to form these compounds. And valence electrons are involved in the bonding. They're very, very important. Remember, those are the electrons in the outermost energy level. Atoms are most stable when their outer energy level is full. So they're going to do things with their valence electrons in order to get full, whether that's losing or gaining or sharing these electrons. So they're held together by these chemical bonds. The goal is to fill that outer shell. So we're going to have three bonds that can happen: ionic, covalent, and hydrogen. Now there's more, but these are the three main types we'll talk about in this class. So let's talk about covalent. Covalent are formed when atoms share pairs of electrons. So think co means together. So we're sharing. These are molecules, and they're always forming between non-metallic elements. Ionic bonds are different. Ionic bonds we're going to transfer. We're not going to share, but we're going to gain or give away electrons. And they go from the metals are going to lose electrons, and the nonmetals are going to gain. Because as you can see looking at this sodium, it has one valence electron. It's a lot easier for it to lose that one electron than it is for it to gain 7 to be stable. Whereas chlorine has 7 valence electrons. So it's in its benefit just to gain 1. So that's what we're going to see happen when sodium and chlorine form. Sodium chloride, or table salt. Atoms will lose or gain electrons. If you lose an electron, you become more positively charged. If you gain an electron, you become more negatively charged. We call these atoms that have gained or lost electrons ions. So this would be an atom, or an ion, of sodium. This would be an ion of chlorine, which is why it forms an ionic bond. Ions can be cations or anions. A cation is when an atom loses an electron, it becomes more positive. So a sodium atom would lose an electron, it gives it a positive charge, so it's a cation. Whereas an anion is going to gain an electron and become negatively charged. So if a fluorine atom gains an electron, it creates a negative ion or an anion. Really briefly, states of matter. I love this picture. Atoms are in constant motion. We call this kinetic energy that they all have. How quickly they're moving determines its state, or how crazily they're moving. So gases are really moving crazy. They're really, really, really spread out. Liquids are, sliding past each other, whereas solids are pretty frigid and pretty rigid in their structure. We call them usually in a crystal structure. They're kind of vibrating next to each other, not really moving much. Now, let's relate all these words to biology. Levels of organization. So we talked about, we got these subatomic particles, these protons, electrons, and neutrons. Those make up atoms, like an atom of oxygen, or O. Atoms are of elements, so again, an element is O. Elements can combine to form molecules, like O2. Macromolecules are just really big molecules. There's 4 of them. We'll talk about them in concept 3. Macromolecules exist in cells. Cell is the most basic unit of life. So cell is the first level in this organization where life is actually existing. So an example would be like a blood cell. Cells build together into tissues. So cells that work together for a common function make up a tissue. For example, like epithelial tissue. Tissues build into organs that work together for a common function. So a bunch of different tissues can make up like an organ like the lung. A bunch of organs working together for a common function could be like your respiratory system, which would be all of the different organs that work together to help you respire. And then organ systems make up an organism like a human or a Homo sapien. All right, that is our really, really quick 15-minute summary of chemistry basics. Now what's really, really important for biology and what we're going to be learning are these properties of water. So we're going to use some things we just talked about and connect them here as we talked about 5 really important things about water. So water is 1 atom of oxygen and 2 atoms of hydrogen. They're held together by a covalent bond, and that compound is H2O. Water is a polar molecule. So what this means, it has an unequal distribution of charges. So if you look kind of at this picture, the hydrogen ends are a little bit more positive and the oxygen is a little bit more negative. Although the whole thing is overall neutral, we kind of see this positive end and this negative end, which makes it polar, and that matters. When water molecules are close together, their opposite sides are attracted to each other because of the polarity. So the hydrogen positive side of one water would be attracted to the negative oxygen side of a different water molecule. And this is responsible for a lot of the properties we see of water. So let's just pause about polar and nonpolar molecules before we move on. Again, polar molecule, there's an unequal distribution of charge. This allows it to dissolve in water because water is also polar. A nonpolar molecule, there's no separation of charge, there's no positive or negative ends. They do not dissolve well in water because they are different from water, which is a polar molecule. Carbon dioxide, oxygen, lipids, these are things that are nonpolar, so they just don't dissolve well in water. And we'll talk about those more in the future. All right, so looking at water molecules, polar water molecules can be attracted to each other. The hydrogen atom with its partial positive charge is attracted to the oxygen that's partially negative of a different water molecule. And this is what creates a hydrogen bond, which is pretty weak, but it still is a bond. So if you look at this picture, it's really good. It's showing the bonding between polar molecules. So you can see this positive part of this hydrogen is attracted to the negative part of this water molecule, this oxygen. So we've got these hydrogen bonds forming. You can see how they're kind of oriented towards each other. Again, so if we actually look at an actual water molecule internally, there's covalent bonds that hold the H's to the O's. But if we look at a glass of water, between each water molecule there'll be weaker hydrogen bonds, which are external, which are represented by these dotted lines. So again, this is showing one water molecule and the covalent bonds within it, whereas these dotted lines between different water molecules are hydrogen bonds. All right, there are 5 characteristics of water that make water really special. We're going to talk through each one and then we'll be done. First is cohesion. Co again means together. This is an attraction between molecules of the same substance. So water molecules, like other water molecules, they tend to stick together. This causes really high surface tension. And surface tension measures how difficult it is to stretch or break the surface of a liquid, how resistant it is to an external force. So you can see that here. These water molecules like to stick to themselves. Now, adhesion is a type of attraction that happens between 2 different molecules. So glass, soil, plant tissue, cotton, etc. It's a stronger bond than cohesion. But this is what we see in the meniscus in a graduated cylinder when it kind of curves on the sides because the water sticks to the sides of the graduated cylinder. This creates capillary action. We see this in plants and trees. You can see this in straws, and this will be really important if you ever take anatomy. Now, the high specific heat of water is super important for life to exist on Earth. Because water has a really high specific heat, it means the temperature of water does not increase or decrease easily. It takes a lot of energy to change the temperature of water. So this helps regulate cell temperatures in organisms because the water temperature doesn't change very rapidly. So temperature doesn't fluctuate very much, which allows things to live really well in water. And this also moderates Earth's climate because it buffers the large fluctuations in temperature. You know, when you're at the beach, you can be at the beach in October and the water is still pretty warm because it takes a long time for that water temperature to change. 4, water has a low density in solid form, which is really interesting. Ice is actually less dense than liquid water, so it floats in liquid water. And since it floats, life can exist under frozen surfaces of lakes and polar seas, which is pretty cool. And last, water is a solvent. So solvent refers to solutions. Remember, a solution is a mixture of substances that looks the same throughout. It has a solute and a solvent. Solute is what's being dissolved, like sugar. Solvent is the water, it's what's doing the dissolving. It would make a solution like sugar water. Water is known as the universal solvent because it's so good at dissolving things in itself. And then there's another example of solute, solvent, and solution. Last slide! Hydrophilic versus hydrophobic substances. Hydro refers to water. Philic refers to liking or loving. Hydrophilic substances have an affinity for water. They like water. They're water-loving. So they dissolve well in water, like salt and sugar. Those are hydrophilic substances. They like water. A hydrophobic substance is afraid of water. So it does not like water. It is water-fearing. It does not dissolve well. Like you can see this oil in the water. They're separated. Hydrophilic substances tend to be polar, like water. Hydrophobic substances tend to be nonpolar, which is not like water. And that is your super quick summary of the chemistry of life and properties of water.